In 2003, the ISS hit a sudden and catastrophic halt in its decade-long construction process. The Space Shuttle Columbia disaster sent shockwaves through the space launch industry. The Space Shuttle was the only vehicle capable of hauling the massive building blocks of the ISS into orbit. With a cavernous 18-meter cargo bay and powerful engines, it could carry entire station modules weighing more than 20 tons at a time. The station's assembly froze mid-construction. Its growth paused in silence above the Earth for 2.5 years. Without Russia and the Soyuz, the ISS would have been lost. Thankfully, that did not come to pass, and the Space Shuttle would soon return to orbit, with some new improvements. This is how the ISS defied catastrophe and how a fractured alliance of nations and a grounded fleet still managed to keep humanity's most remote outpost alive. This is the insane engineering of the ISS. Part 2. While engineers on the ground were scrambling, looking for clues to try to find the culprit of the Columbia disaster, NASA had to look up to the skies as well. The ISS was not meant to fly uncrewed. The 3 astronauts on the ISS had to wait 2 months before the next Soyuz arrived to rotate the team. 3 returned home, 2 stayed behind to keep the station alive, the safest minimum crew size. Now it was time for the ISS to go into power-saving mode. Experiments were cut, and the lonely crew kept the station running for as long as possible. With the cargo capacity decimated, water and food were prioritized. These were the station's lifeline, the Russian Progress resupply ships. The day after Columbia, one launched with food, water, and essentials. 2 months later, the next cargo ship would arrive. Normally, once a new Progress arrived, the old one would be released and sent back to burn up in Earth's atmosphere. This time, instead of discarding the previous Progress ship, they kept it docked. Every bit of extra space could be used for food, water, and spare parts, critical for the station's survival plan. Parallel to figuring out how astronauts were going to live aboard the ship, it was imperative to get the shuttle back in operation and safely. On the ground, they ramped up launch monitoring. NASA deployed high-speed tracking cameras around the launch pad, and they installed onboard sensors to detect foam impacts in real time. During the very first mission after Columbia, STS-114, 16 pieces of foam came off the external tank during launch. One of them was quite large, around 91 by 30 centimeters. Before Columbia, there was no way of knowing how much foam impacts affected the heat shield. So, a new system was set up to inspect the thermal protection system of the shuttle once it was in orbit. This is the Orbiter Boom Sensor System. It is a long 15-meter boom that could be attached to the shuttle's canadarm, outfitted with lasers and high-resolution cameras. The idea was to let astronauts scan the shuttle's heat shield tiles and reinforce carbon-carbon panels on the wings and nose cap. This is footage from the boom sensor aboard the first shuttle flight after Columbia. Discovery also performed the very first rendezvous pitch maneuver before docking with the ISS, essentially a backflip that allowed the ISS to take hundreds of photos of the underside to inspect for damage. That same mission included 3 spacewalks, one to replace the old gyroscope and the other 2 being newly developed safety procedures. Dangling from the end of the Canadarm2, an astronaut was tasked with inspecting the space shuttle, and they actually physically removed 2 gap fillers that had started to protrude from Discovery's underside. Had those fillers remained, they could have created dangerous hotspots during re-entry. The next spacewalk was designed to test new on-orbit repair techniques. Samples of heat shields with simulated damage were stored inside Discovery's payload bay. Spacewalkers were tasked with injecting sticky sealant into the cracks using hand tools. Shallow scratches were filled with a liquid wash that soaked in and restored heat resistance, while deeper gouges were filled with a thick paste that hardened in orbit. All these samples were returned to Earth to confirm their effectiveness. The spacewalks proved that even if the shuttle was damaged, astronauts could inspect and repair the heat shield in space. By September 2006, the shuttle was finally cleared to restart building the ISS, and it was in desperate need of more power. The portside solar panels came up first. Half of the P6 panels were retracted to make the station symmetric and to avoid collisions as the new solar panels span around. Next came the starboard side. The solar arrays on the ISS are stored in folded blankets inside rectangular boxes mounted on the truss. Each wing consists of 2 blankets of solar cells attached to a central mast. A motor drives the mast outwards, and as the mast extends, it pulls the folded solar cell blankets out with it. Guide wires run through reinforced holes along the blanket to keep the structure aligned and under tension. Each truss also carries its own ammonia cooling loop and radiators to keep the panels from overheating. Then came STS-120 in October 2007, a mission carrying the second node of the system, Harmony. Harmony was initially attached here to the starboard side of Unity, so it would be out of the way while the P6 solar array was relocated. Canadarm2 reached out and grabbed the truss segment here, just above the station, but it couldn't carry it all the way to the far end of the ISS, so the arm passed it to the shuttle's Canadarm. From there, Canadarm2 moved along the mobile-based system to the station's edge, took the truss back, and guided it into alignment. Then, 2 astronauts stepped outside to bolt it into place. One of them was Dr. Scott Parazinski.
We'd been out at the very tip of the space station. We had, working with Dan Taney and Stephanie Wilson, who were driving the robotic arm. We were able to bring the P6 truss in close proximity to the P5 truss, and we were able to bolt the thing together. We mated the electrical connectors. We thought that the most challenging part of the mission had been accomplished. We were starting to celebrate, but we were wrong. This is when it really got exciting. So as we got out of our spacesuits and floated into the laboratory module, we saw everyone hunkered around this small CCTV monitor trying to see what was going on. And we couldn't really see the details, but it looked like there had been a rip in the solar panel. And this was at a position where the solar panel was only partway deployed, and we couldn't retract it at this point, we couldn't extend it.
This is what the situation looked like. One of the solar panels did extend, but the other side only extended 80% of the way. From the window of the ISS, they could see a small hole in the solar panels, but they couldn't really tell what had happened. The first obstacle was distance. The torn array was located far from the normal reach of the Canadarm2. The only option was to attach an astronaut to the long boom used to inspect the bottom of the shuttle, and this carried a lot of risk. First off, solar panels in space don't need to hold their own weight, so unlike panels here on Earth, the panels on the ISS are a lot wobblier than you might imagine.
Yeah, these aren't your mom's and dad's solar panels that we have aboard the ISS. They're quite unique. They are mounted on thin film, so they're basically circuit boards that are hinged, sort of like leveler blinds that you might have at home. But they're very, very flexible. And in fact, if you were to push on the solar panel in its partially deployed state, it would float away from you very gracefully like a sail, but then ultimately it would work its way back. And in fact, that was one of the major concerns that they had for sending a spacewalker out there, because this solar panel was likely damaged. And so there were concerns that there could be arcing of electricity, high voltage, high current, from the solar panel into my spacesuit. And of course, my spacesuit has a Kevlar outer, but there are metal wrist disconnects and other metal parts of my spacesuit that could allow for electricity to conduct into the 100% oxygen environment of my spacesuit, which would be very flammable. It'd be a very bad day for me. So engineers very graciously thought about my safety. So we ended up wrapping the metal parts of our spacesuits for both Doug and myself with Kapton tape, so that there would be no risk of conductance of electricity into our spacesuits. And then we weren't able to have any direct contact with the solar panel. So I actually had I've got one over here, I think. Yeah. So this is kind of interesting. This is a hockey stick, very similar to what I used in space. And so this is not the real one, but it's made of the same materials. It's got a tether loop on the tail of it. But I would use this tool, stick in front of me such that the solar panel would pass harmlessly above my head and beneath my feet.
From the images and from talking to the astronauts, the team on the ground had already figured out the problem and a potential solution. The guide wire running along the solar panels had been damaged, so Scott needed to get out there, cut the guide wire, and reconnect them with a MacGyvered repair using materials available on the ISS.
And then I have here, actually, one of the engineered cufflinks that was used on 1G mock-ups of the solar panel here in Houston. So this is actually what it looked like. This is one of the shorter ones when we had a couple of much longer ones as well that I installed. This allowed me to poke this through a hole in the solar panel on one side of the damage, and then this one ended up going on the other side, and then the load path could be absorbed by this piece of wire. But the really cool thing, and this is one of my prized possessions, this was given to me by the engineer who invented this repair. And this is actually 2 pieces of cardboard from a Domino's pizza box. They were working around the clock. They worked for like 72 hours straight. But this engineer had this idea for these cufflinks, and he cut a Domino's pizza box, tied it together with a couple of pieces of string, and he threw it on the table and said, "Here, what do you think about this?" And that became the solution to save the solar panel.
That's crazy. I guess my question is, like, do the people on the ground have like a full inventory list of what's up on the ISS? Like, how do they know what you can actually build?
Yeah. Well, they knew exactly that we had this 12 gauge wire aboard the space station. This is aluminum shim stock that's been covered in tape, so it wouldn't conduct. This is a threaded fastener that we had in stores. So they know exactly what we had aboard the space shuttle and space station inventory, and that became the shopping list. You need to go to such and such a location aboard the space station and get out the reel of 12 gauge wire, and then they created a procedure around that to allow for the assembly of these things. And they had to be measured incredibly precisely. So this couldn't be too thick, or it wouldn't go through the solar panel. It couldn't be too long, or it wouldn't pass through. The length of it had to be measured exactly to spec.
So, with the cufflinks made and Scott's wrist wrapped in insulating tape, it was time for the mission. He left the ISS through the Quest airlock and spacewalked his way to the edge of the ISS. Here is where he would be picked up.
Yeah, so I was picked up on the truss of the International Space Station using this, as you mentioned, the Canadarm2 and the orbiter boom sensing system inspection boom. And then I had a 45-minute commute, and it was a wild ride because it's a very ungainly robotic arm system that was at risk of hitting other solar panels, hitting the other parts of the space station. And of course, they didn't want me to get anywhere close to the proximal solar panels that we had to kind of work around. So it was a very complex maneuver that Stephanie had to fly me on. And I remember vividly, we were all together. This is a day before the spacewalk, hunkered together in the joint airlock. My crew with Pam and Paolo, Stephanie, and Dan, and George, and Doug, as well as the ISS crew. And they had created this animation of this extraordinary long arc and how the whole arm was going to be reoriented. If a pin could drop in space, you would have heard it. It was there was just all of our jaws were dropped. We couldn't believe that we were about to go do something as wild as this. But miraculously, the plan that they came up with was a home run.
From his helmet camera, you can see the mission unfold. Once he got into position, he got straight to work. He cut the guide wire and started to sew in the cufflinks. One by one, Scott installed 5 cufflinks into the solar panel in a tense 7-hour mission outside the station. But it worked. The array extended fully, restored to full functionality. This repair remains one of the most complex spacewalks ever performed. And to this day, the solar panel on P6 has those cufflinks Scott installed. So did we ever actually figure out what caused the damage to the guide wire in the first place?
I can't find it right now, but they actually gave it to me. It was really, really cool. After I cut out the piece of frayed guide wire, we have a trash can. It's just a tiny little pouch. So I was able to store that, bring it back inside, and ultimately back to Earth. It was sent to a laboratory, and they did analyses on it and determined that there was a tungsten, which is clearly a man-made object, had come in contact with this steel braid cable and had clipped probably 2 of 7 steel braids, steel strands. So it's amazing you can actually do that kind of sophisticated analysis on a tiny little piece of steel braid cable. But it was clearly as a result of a man-made object striking this guide wire in a unique way.
This is what makes building in space so unforgiving. All it takes is a fragment, a tiny shard from an old satellite, racing around the Earth at thousands of kilometers an hour. By pure chance, it struck the ISS. The damage was small, but the risk was enormous. After this successful repair, Harmony was relocated to the forward end of the Destiny lab. The pressurized mating adapter 2 was then reattached to Harmony's front end to serve as the new shuttle docking port.
So what would have happened if you didn't fix the solar panels?
Yeah, there's a lot of conjecture there, and I don't know what mission managers would have ultimately decided, but there was talk of us having to go out and jettison the solar panel. That was the next thing that we would have had to have done to make it safe for us to undock. The concern was, there's quite a bit of momentum exerted when the shuttle undocks, and then there are jet thrusters that are fired, and those might have somehow interacted with the limp noodle solar panel out there and ripped it apart. So it's likely that we would have gone out on another spacewalk, thrown it away, and on a subsequent flight probably launched another solar panel, for the main reason that the space station program was really critical to the power generation of that solar panel. There are European and Japanese modules that were just about to be launched. It wouldn't have really been possible to support them without that additional power.
Europe and Japan wanted their own facilities where their astronauts could run experiments, test new technologies, and bring home results for their own space agencies. STS-122 in February 2008 brought the answer: the European Columbus Laboratory. Carried into orbit aboard Atlantis, Columbus was attached here to the starboard side of Harmony. 2 spacewalks connected it fully. With this single module, Europe gained a permanent orbital research hub. But scientific research wasn't Europe's goal alone. Japan had its own ambitions and its own module, Kibo. The core pressurized module of the Kibo complex arrived in May 2008 on STS-124. It is the largest module on the ISS and is installed on the port side of Harmony. Earlier flights had already delivered the logistics module and the Japanese robotic arm. With this final piece, and after several spacewalks and robotic operations, Japan's vision of a complete research facility in orbit became real. With the science labs needing extra power, it was finally time to bring up the last of the large solar panels, bringing the station to full power by March 2009. But the solar panels on the ISS are not fixed in one position. The station orbits Earth every 90 minutes, and its angle to the Sun changes constantly. Huge rotary joints rotate entire truss segments, making a full turn every orbit to keep the panels facing the Sun. The Sun's angle also changes as Earth orbits around the Sun. Beta gimbal joints make vertical adjustments like this. The daily adjustment is about 4 degrees, but over a year, the panels can move up to 70 degrees. This is where the 51-degree orbit began to cause problems. The panels were designed for the US-only Freedom Station with a 28-degree orbit, where every pass took it regularly into Earth's shadow. But the 51-degree orbit of the ISS means at certain times of year, the station stays in constant sunlight for long stretches. In those periods, the low angle of the Sun causes one set of arrays to cast shadows on the others, cutting power. Even worse, parts of the same array can be in shadow, while other sections and their supporting beams take the full heat of the Sun. These beams that give structure to the wobbly solar panels are vulnerable. Even 20 minutes of uneven shadowing can make sections heat and expand at different rates, twisting the mass and risking damage to the entire array. Solar panel arrangement is an optimization problem. While NASA came up with their solution, they opened up a $30,000 prize to whoever could create a program that would optimize the solar panel's position while preventing problematic shadowing. This is what they came up with: a smooth turn of solar panels with slight delays to avoid these shadows. This is what the station looked like by July 2009. The station had come a long way, but more was coming up. One key capability was still missing: exposure to open space. In July 2009, STS-127 delivered Kibo's exposed facility, installed using both the Japanese arm and Canadarm2. Mounted outside the Kibo module, it finally let researchers expose materials, equipment, and living organisms directly to the vacuum of space. As operations grew more complex and long-term stays became routine, astronauts needed better life support and living quarters. STS-130 answered that call in February 2010 with the delivery of Tranquility. It was mounted to the port side of Unity. Tranquility brought new air revitalization, water recycling, and exercise equipment, but it also came with something else, just for fun: the cupola, an incredible panoramic viewing module that made life on board the ISS much more enjoyable. But installation didn't always go smoothly. Initially, the cupola was attached to Tranquility like this, not in its final location. Once in space, the plan was for astronauts to attach a thermal cover over the cupola and position it here. But astronauts were having a hard time placing the thermal cover. The tolerances were much tighter than expected. Bolts weren't included in the 3D models of the cupola to save memory on the file, which meant the digital mock-ups didn't show how little room actually existed for installation. To make it worse, the team realized that the cupola had been the only module mated with another module on Earth, so the extra gravity made the bolts even tighter than expected, which caused several bolts of the common berthing system to jam during relocation. This led to tense last-minute calculations and meetings to ensure the cupola would fit without structural damage. With all of those setbacks out of the way, the cupola was finally moved to its final location here on the nadir port of Tranquility. The cupola's 7 windows give astronauts an incredible view while keeping them safe from the harsh environment outside. Each window is composed of an inner scratch pane, 2 thick pressurized panes, and on the outside a debris pane shield. When not in use, the windows are protected by manually operated shutters that the crew open and close with a simple hand crank. This is a mechanical connection. The shaft that turns the shutters runs straight through to the vacuum of space. Only 2 O-rings stand between the interior atmosphere and the void outside. Then came STS-135, the final space shuttle mission. It brought up the Raffaello module, packed with spare parts, tools, and supplies to sustain the station in a post-shuttle world. After the shuttle's retirement, expansion continued through Russia's launch services. In July 2012, they launched the Mini Research Module 1, Rasvet. Attached to the nadir port of the Zarya module, it provided cargo storage and internal workspace. But relying on Russia was not in the United States' best interest. This was the beginning of a new era. The commercial space launch industry was about to rapidly expand. In January 2014, the Cygnus CRS-1 mission delivered a large batch of supplies and experiments aboard an orbital sciences vehicle. Around the same time, SpaceX Dragon missions also became a regular part of ISS resupply and hardware delivery. By 2015, the station had become fully operational. It had multiple research labs, robotic systems, observation windows, and docking ports. This technically marked the end of the original construction phase for the ISS, but more was coming. The old shuttle-era androgynous docking system had done its job for decades, but it was big, heavy, and designed only for the space shuttle. With new commercial spacecraft on the horizon, NASA needed something universal. That change came with the International Docking Adapter. It uses a modern androgynous system, but instead of a mechanical slam, the adapter uses a soft capture system. As a spacecraft approaches, guidance sensors and small alignment petals gently draw it in. Once contact is made, active latches close slowly and pull the vehicles together for a tight, hard seal. The process is fully automated, far smoother, and safer for both vehicles. Technically, the adapter is smaller. The docking tunnel is 0.8 meters wide, but the adapter's overall mass and complexity are much lower. It's also equipped for power, data, and fluid transfer between vehicles, something the old androgynous shuttle system couldn't do directly. The first adapter was launched in 2015 aboard a SpaceX Dragon capsule, but never made it, lost in a launch failure just minutes after liftoff. A year later, the second adapter reached orbit, packed inside the unpressurized trunk of a SpaceX Dragon. Once at the station, the Canadarm2 pulled it out and carefully positioned it on the front end of pressurized mating adapter 2 attached to the Harmony module. The third built adapter arrived in 2019 aboard another Dragon. Together, the 2 ports, one facing forward and one facing zenith, now serve as the main gateways for Crew Dragon and Boeing Starliner. For the first time since the shuttle era, America had a way to bring its astronauts to the station on its own vehicles, using a docking system designed for the future. It was now time to start experimenting with new ideas. Back in the 1960s, NASA had explored inflatable living spaces under a project called TransHab, meant for deep space missions. When the program ended, Bigelow Aerospace acquired the NASA patents and revived the concept, developing it into a commercial line of expandable space modules. Launched on April 8, 2016, the Bigelow Expandable Activity Module, or BEAM, rode to orbit folded inside the Dragon's capsule's trunk. Once docked, the Canadarm2 reached in, pulled the compact cylinder free, and attached it to the aft port of Tranquility. At first, BEAM was only 2 meters long and 2.5 meters wide, a small folded package. Once expanded, it grew to about 4 meters in length and 3 meters in diameter. Unlike the rest of the station's metal modules, BEAM was made of layers of fabric, Vectrin, Kevlar, and other high-strength materials designed to protect against radiation, micrometeorites, and temperature swings. Inside, a flexible bladder held air and gave the module its shape once inflated. What was meant to be a 2-year test kept going, and today, BEAM is still attached to the ISS, used for storage and data collection. More importantly, it proved that soft-sided habitats could work, paving the way for future space stations, lunar bases, and missions beyond Earth orbit.
As an engineer, the battle between Windows and macOS isn't always just an issue of preference, it's an issue of productivity. Most engineers use Windows, and that's because there are countless engineering programs that just don't have a macOS build. SolidWorks, one of the most popular design softwares, is Windows only. That's annoying if you prefer macOS for certain tasks. When I'm traveling, I much prefer my Mac. It's reliable and it's light, and it works really well on my phone. I can take a video on this and just airdrop it straight to my laptop. I've always wanted that kind of connectivity between my Mac and my PC, and when the sponsor of this video reached out, I found out you could, because I literally just installed this program to write this ad, and I was sold within 5 seconds. It took me 5 minutes to install on my PC and Mac, and now I can use my PC's keyboard and mouse on my Mac. Look, my mouse cursor even transfers over from my Mac. That's incredible, and there are so many ways I could use this. I wouldn't even need to be near my second screen. Synergy is a software that lets you control all your nearby computers with one keyboard and one mouse. No dongles, no hardware boxes, no cables, and no cloud service. Just install it, sign in, and all of your machines discover each other automatically over your local network. Then you drag them into a layout, choose which one is the primary, and that's it. When your mouse hits one edge of the screen, Synergy instantly hands control to the next computer, like all your machines have merged into one seamless setup. And because it has a universal clipboard, you can copy and paste text and images between Windows, Mac, and Linux like they're all running on the same operating system. And all of this happens on your local network. Nothing gets sent to the cloud. Honestly, I'm so glad they reached out to sponsor because it's how I found out about them. And I'm honestly excited to share this software too. If you want to try it yourself, visit our link or use the discount code REALENGINEERING and get 50% off.